Hi everybody, my name is Fabien Appert and I will talk to you about EyeSat and how it was a great student adventure within the French Space Agency and what lessons we learned from orbit. EyeSat is a student 3U CubeSat. It was developed at CNES, the French Space Agency, and it was launched on December 18, 2019 on a Soyuz rocket from the French Guiana. You can see right here the logo on the rocket. And since then, the CubeSat is fully operational and functional, and I will show you in this presentation the lessons we learned from it and how it works in orbit. First of all, the first objective of EyeSat is education. We wanted to produce a triple CubeSat with students in order to promote space engineering. Then there is a science objective. We want to observe the zodiacal light, which is the solar light scattered by interplanetary dust particles. And we do measurements of the intensity and of the polarization direction of this light within 4 spectral bands: blue, green, red, and near infrared. You can see on the right a picture of the zodiacal light, which is this faint and white halo that you can see in the center of the picture. And finally, there is an outreach objective. We want to do a 360-degree image of the Milky Way. To do that, we developed a specific payload. You can see on this slide a CAD view of the payload. Beginning on the right, we have a camera with a color CMOS detector inside. Then we have a 2-stage filter wheel. So there are 2 wheels rotating in opposite direction. On one wheel there are visible and near-infrared filters, and on the other wheel there are polarizing filters. And finally, there is a COATS optics. On this slide you can see actual pictures of the payload. And on the bottom right, you can see a movie of the payload with the 2 wheels rotating and with the filters passing behind the optics, which is quite cool. Here are 2 pictures taken by our CubeSats. The first one on the left is a picture of Andromeda galaxy. The galaxy is right in the middle of the picture. And the second one is Lake Moeris in Australia. Of course, when you have an imager in space, the first thing you want to do is to turn it towards the Earth, down to the Earth, and take a picture of it. That's what we did very quickly after the injection on orbit, and this is the first picture we took of the Earth. Let's have a look at the satellite. I will not go too much into detail with it. There was a paper published at the SmallSat conference last year in which you can read all the technologies that are inside EyeSat. The main features we can notice are the 3-axis pointing, the X-band telemetry with a high data rate, the S-band telecommand and telemetry. We have 4 deployable solar panels. The onboard computer is based on a zinc system on chip. And finally, the flight software was developed with a time and space partitioning technology. So, first results. It is commonly said that knowledge is power, but maybe it is also the opposite. Here you have a graph of the battery's voltage versus time at the very beginning of life of the satellite. This is the first 300 minutes of life. And you will see that with only one parameter, we can get a lot of information of what happened on board. So first, at the beginning of the graph, you can see a very fast variation in the voltage. This corresponds to the phase where the solar panels were stowed along the sides of the CubeSat, and the CubeSat was rotating. So sometimes we had more sun on the solar cells, sometimes we had less sun, and this led to those variations in the battery's voltage. And then you can see a very big decrease in the voltage. This is when the thermal knives activated themselves and the solar panels were released and were deployed. So there was a lot of current in the thermal knives, and so the battery voltage went down. Then you can see the ADCS convergence, and we had our first eclipse. So during the eclipse, the voltage went down, and at the end of the eclipse, it went up very quickly, up to its limit of 8.2 volts, which is the limit when the batteries are fully charged. Then we had a second eclipse, which is very interesting in this second eclipse is that the temperature went down inside the satellite, and so the battery heaters activated itself to heat up the batteries. And then again, at the end of the eclipse, the voltage went up again. And then you can see those small variations, those small drop in the voltage. This is the radio frequency cyclic modulation we have on board. Indeed, when we are in safe mode, and this is the mode in which the satellite starts, when we are in safe mode, we do 1 minute of emission, of radio frequency emission, every 5 minutes. And this is what we can see in this graph. And then we had a third eclipse. So these, with only one parameter, we can see a lot of information. Let's have a look to another subsystem, the attitude determination and control subsystem. The pointing accuracy is better than predicted. We do have an astronomy mission, so we do have a harsh requirement concerning the pointing accuracy. We wanted to achieve a 0.25 degree pointing accuracy. What we achieved in reality is better than 0.1 degree. That's you can see that on the graph on this slide. This graph shows you the onboard estimated pointing accuracy. So 0.1 onboard estimated pointing accuracy is very good, but it's not enough. Why? You can see on this picture, we took a first picture of Andromeda, and of course we wanted to have Andromeda, the galaxy, in the center of the picture. But you can see that Andromeda, which is in the red circle, is not really in the center of the picture. And why that? Because we have a misalignment between the star tracker, which is the reference for the pointing, and the payload. So for the second time, we took into account this misalignment. And this is the second picture we took of Andromeda, and you can see that this time the galaxy is right in the middle of the picture. So the pointing accuracy of 0.1 degree is absolute, which is really nice. Then, is it hot or is it cold in the CubeSat? Well, I show you here two graphs. One is a prediction and another one is actual data of the temperatures of two components, the onboard computer and the magnetorquers. Actual data tell us that the mean temperature aboard is around 10 degrees Celsius, which is quite comfortable. And what is very interesting is the mean difference between the prediction and the reality. And the mean difference concerning those temperatures is around 6 degrees Celsius, which is very good. Well, of course, we have other temperature points within the satellite, but I cannot show you everything in only 15 minutes. And now the adventure continues. Indeed, EyeSat gave birth to a private company, which is called EyeSpace. EyeSpace designs, builds, and operates nanosatellites based on the technologies we developed with EyeSat. We have three main commercial offers. The first one is the manufacturing of nanosatellites. So we design, we build, and we test nanosatellites. Then we can also take care of the launch and the operations of the nanosatellite if you want. And finally, if you just have an idea of what you want to do, of what your mission could be, but it's not very clear in your head, we can help you with preliminary study in which we do a preliminary design of the mission and of the nanosatellite, and we estimate the cost and the development time to do the complete mission. So thanks everybody for listening me. I invite you to check out the full paper in which you will see a lot of more information about what we learned from EyeSat. Maybe see you next year at the SmallSat conference. Bye bye.